Okay, ladies and gentlemen, let's start talking about special right triangles. Now, we've already talked about what a right triangle is. A right triangle is a triangle that has one right angle in it. Now, that's very important because with a 90-degree angle in it, there are a number of special things that begin to take place. The first of which is we can use the Pythagorean theorem. The Pythagorean theorem. And the Pythagorean theorem, of course, is leg squared plus leg squared equals hypotenuse squared. Now, this becomes very important because we have these things called Pythagorean triples. So the Pythagorean triple, we've talked about it. That's where you have three numbers that would make the Pythagorean theorem true. So example 3, 4, 5, you have a triangle with a side of 3, a side of 4, and a side of 5, and that does indeed make a right triangle. You also have 5, 12, 13, so it looks something more like this. You have 5, 12 over here, and of course 13. We know that 13 has to be the hypotenuse because the hypotenuse is the longest side of the triangle, so the 13 has to be there. But we also have two that are just even more special beyond that. Not only are they Pythagorean theorem triples, not only are they right triangles, they're a special type of triangle. And those triangles are a 90, 45, 45. So a 45, 45, 90 triangle. These are even more special than the others because we also know their side relationships of 1, 1, and root 2. 1, 1, and root 2. You need to memorize this triangle. Okay? The other triangle is a 30, 60, 90. Now you'll notice in both triangles, all the angles, of course, add up to 180. But the ratios of the sides are what's important. Across from the 30 is 1, across from the 60 is root 3, and across from the 90 is 2. There's a couple reasons for these, and let's get into them. Now, if I were to take a square, everybody can agree that a square has 4 right angles, 1, 2, 3, 4, and that all sides are the same. Now, here's the deal. If I draw a diagonal in here, what did I just do to this angle and this angle? The answer, of course, is I bisected it, meaning this is 45, and this is 45, and this is 45, and this is 45. It's one of our theorems. You also notice that because it was a square, these two sides were already congruent. So one of the reasons my 45, 45, 90 triangle is so special is because we already know those two sides are congruent. We already know it has a 90-degree angle. And so now with the 45s involved, because if the sides are congruent on an isosceles triangle, what has to be true about the base angles? They also have to be congruent. So we have a 45, 45, 90 triangle. If I set this equal to x, if it's x inches, x feet, x miles long, this side up here has to be x feet, x miles, x inches, because if this is congruent to this, if this is x, this is x. Now, how would you find the missing side? Well, a squared plus b squared equals c squared, so I say x squared plus x squared equals c squared. Well, what's x squared plus x squared? 2x squared equals c squared. And if I square root both sides, the answer is square root of 2 times x equals c. So you end up with root 2x. And so now if I have a triangle down here, and I know this is true, automatically you could tell me, 45, 45. Okay. And if I told you this is 7 inches long, automatically you say, wait a minute, 45, 45, 90 triangle, it has to be, if this is 7 inches, this is 7 inches, because if this is, this is. And what does this have to be? It has to be root 2 times 7, or 7 root 2. So that's how you use these special triangles. You use them based on similar triangles to make other sizes. I don't like the x's because we'll use x's in other places. I traditionally just say the following. If I have a 45, 45, 90, and this is 8, I don't even have to have another triangle. I know my generic 45, 45, 90 is 1, 1, root 2. So I can say 1 is to 8 as, I don't know, R, as root 2 is to R. And I can cross multiply and I get 8 root 2. Again, I could come over here and say, well, wait a minute, if 8 is to 1, then 8 has to be to 1 here. So whether you think about it like x's, whether you think about it just like a stock ratio that you can always use proportions with, it all works the same way. Now, let's also take a look. I told you there was another one, and that's a 30, 60, 90 triangle. Now, this does not come out of a special shape like a square, but what it does do is if we know any triangle where the hypotenuse is twice as long as the shortest side, hypotenuse is twice as long as the shortest side, then the third side has to be, well, let's figure it out. Leg squared plus, leg squared I don't know, equals hypotenuse squared. 1 plus x squared equals 4, minus 1, x squared equals 3, x equals the square root of 3. We don't use the minus version because it's a distance, so we only care about the positive. It is square root of 3. Now, the other way to think about this is the square root of 3 is about 1.7. One of the biggest mistakes people make is they want to do it this way. They want to say 1, 2, and root 3 because they say 3 is bigger than 2, 3 is bigger than 2, 3 is bigger than 2. No, it's not, because it's square root of 3. The square root of 3 is 1.7. And we know in a triangle that the biggest side, 2, has to be across from the biggest angle, 90. The next biggest side, 1.7 or square root of 3, has to be across from the next biggest angle, 60 degrees. And finally, the smallest side across from the smallest angle. So this is not right. Now, even if I turn it up like this, if I give you 90 and 60, and I tell you that this is 1, automatically you know, square root of 3 and 2 and 30, because I can do this by subtraction. I know that in a 30, 60, 90, if this is 1, this is root 3. But let's do it again with something a little different. Let's say I tell you this is 6. Oh, well, how do I find x and how do I find y? Well, I could say 1 is to 6 as root 3 is to x. So you notice I went little triangle to big, little triangle to big. It has to be in some sort of proportion. We're not going to get out from doing these proportions, so we might as well learn them. So that's 6 root 3. So by the way, what would y be? Well, we could do another one. We could say 1 is to 6 as 2 is to y. And so y equals 12. And there we go. Those are your special triangles. You are going to use them over and over and over and over again. And when you get to pre-calculus, algebra 2, you're going to use them over and over and over again there. Here's what I want you to do. Here's a problem or two. Number 1. If I have a side of 5, find x and y. Number 2, here we go. If I have this and I have 4 root 3 across from the 60, find x and y. There you go. Those are your two problems.